Yep.
Hello everyone. Today we have with us a PhD student from University of Montreal, Krishna Murthy. We're going to discuss his paper GradSLAM, which was recently presented at ECCV. And he's a PhD student at University of Montreal, and his research interests include interplay of robot vision, deep learning, graphics, and physics. So we look forward to your talk.
Thanks. Thanks for having me here, and I apologize for the delay, but I'm trying to go a little bit, pace myself so that we still end on time.
Yeah. No, time is fine, Krishna. Take your time. Don't hurry up. You do, please go according to your pace. No
Sure.
problem.
Thanks. So today I'm going to be talking about some of my recent work. It's called GradSLAM, and the talk is titled Differentiable SLAM. And this is in collaboration with Ganesh Iyer, Soroush Siddharthi, and Liam Paul. Ganesh is from the Robotics Institute at Carnegie Mellon. Liam and myself, we're from Mila, and we're located at the University of Montreal. Soroush Siddharthi is another master's student from Concordia University, Montreal, who is very instrumental in the final stages of this project. So yeah, let's just get started. But before we get into the talk, a bit of geographical info on where I am. Montreal is almost in the eastern, southeastern part of Canada, pretty close to the US-Canada border, and it gets quite cold here in the winter. Like today, it's a rainy day out here, so that's probably why my video is all a bit blurred up.
Yeah.
But yeah, this is our robotics group at Mila. It's the Robotics and Embodied AI Lab. I think we're currently still growing. We're at 24 or so people now. But Mila itself is a very big lab where people work on all sorts of applications related to machine learning. So these were obviously pre-pandemic photos. And now it's just hard to imagine getting another group photo like this. But yeah, Joshua really was behind getting Mila up and running. And what started out as a small lab at the University of Montreal soon expanded to other universities in Montreal, like there's McGill and there's Polytechnique, HEC. So profs from all these universities, as well as their grad students and interns, they make up Mila. So in a way, Mila is much more than just a university. It's sort of a machine learning ecosystem out here in Montreal where people from multiple universities get together, and the environment is quite collaborative. So yeah, with that bit of intro, we'd move further. So one other caveat before we begin the talk, this talk is going to cater to just one very small subset of my research interests. I've tried to outline my three main research areas so far on this slide. So I did quite a bit of SLAM or state estimation research over the past 3 to 4 years. And that involves multiple facets of SLAM using monocular cameras, object-based SLAM, deep learning for SLAM. There's also a few other areas that I'm interested in that I won't be able to talk about today. I have a huge focus on differentiable graphics and physics and how we can leverage those phenomena or rules of the world, which we've studied for so long, and use them to train more efficient models in the context of learning methods. And another significant bit of my research strives to develop perception techniques for autonomous driving. So I've been focusing on, again, leveraging projective geometry, cues, and other things that we already know and incorporate them effectively into neural nets for better perception in autonomous driving. So this is pretty much what I did my master's on, but the first two themes are what I'm primarily focusing during my PhD. So yeah, as a precursor to the talk, I'd like to state two basic assumptions that I have that drive most of my research. And I guess if the talk is looked at in isolation, these assumptions are implicitly baked in at most places. And I think it's just worth focusing or taking a bit of time to understand these assumptions and my rationale behind them. So I tend to believe that robots are the future, and in a couple of decades, we're going to co-inhabit spaces with robots. We're going to have robots in our workplaces, in homes, and outside. And we're already beginning to see some of these changes. For example, if you look at the top, the now robots and the Baxter that you see here, they're still more of laboratory robots. They don't they're not so domesticated, for lack of a better word. The only place you ever see them is maybe research labs or expositions. And these are still, you know, in a way primitive. They don't really co-inhabit spaces with humans. But on the other hand, if you look at the two robot examples at the bottom, so you have self-driving cars that are already beginning to show up in a lot of cities, and they're driving along with human drivers on a few roads. And Boston Dynamics recently started making the Spot Mini robot available to consumers. So this really drives my belief. I think robots will be in 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 a few decades. We'll have robots around us, and that's the future that I'd like to prepare ourselves for. And there's also another distinction that I've seen, especially over the last 5-6 years. There's been a clear distinction between classical and learned robotics, as I call it. So when I say classical, it doesn't really mean that a technique is outdated or a few dozen years old. But what it rather means is that we don't have a lot of learning in here. So when I say classical techniques, I refer to techniques where we have very well understood theory behind all of them. And usually for classical techniques, it's feasible to provide some form of guarantees so they are in a way interpretable. So if you look at the classical approach to robotics, they view they view the robotic stack as a set of submodules, each submodule doing a particular task. For example, perception, estimation, cognition, and action. That seems to be a split most people agree on. So there's this modularized view of classical robotics where each submodule has a particular task that it's cut out to do. And the other paradigm that we've been seeing, especially with end-to-end learning or even model-free reinforcement learning, is that you have one monolithic deep network that replaces everything a robot ever needs to do. So if you look back at some of these examples, you might imagine just having one neural net that directly predicts motor control, the steering angle and velocities from the image observations that a self-driving car sees. There seem to be like two different paradigms, and my philosophy in terms of research is to find a good middle ground between these two. And based on assumption one, where robots are going to inhabit spaces with humans around, it is really important for robots to be able to explain themselves in a manner that's interpretable to humans. So that's one place where modularity really is important. Robots need to make their decisions understandable or interpretable to humans. And the techniques that I'm going to talk about today are a baby step towards finding this middle ground, and they're like one possible way to find an interpretable middle ground. So I'm assuming quite a few people have heard of gradient-based learning or deep learning.
Yeah,
And
you could just give just like one line background.
sure, yeah. So a lot of these techniques have they were incidentally developed several decades ago, but they've only risen to popularity. Uh, like 2012 was really the year when these techniques started gaining widespread adoption. Uh, so deep learning typically refers to having neural networks stacked layers of neural networks that perform some form of computation on input data and give you an encoded output of interest. And traditionally, there have been several techniques developed corresponding to the kind of data used. So for images, the most popular network architecture used is convolutional neural nets. And most of these architectures are typically trained using gradient descent or a variant of gradient descent, which means the network performs a differentiable forward computation, and then you define a loss or a performance metric over the output space of that network. And the error or that performance metric can be differentiated, and the gradient is backpropagated through the network to update your weight. So this is a very common paradigm of training deep networks. And now, in the context of robotics, the task that I'm very interested in and the task of interest today is called SLAM, or simultaneous localization and mapping. So if you just want to unpack this term, you're doing localization, which is in crude terms, it's the where am I question. So if you take a robot, put it in a new house or in a new room of your house, localization corresponds to answering which room am I in and where am I in that room. And then there's another complementary question. It's called mapping. And mapping corresponds to the question, what is around me? So what do I see right now? And this, the answers to these questions can be quite broad depending on the context you're in. Like if all your robot needs to do is identify the room it's in, it's a whole different game compared to, let's say, a robot trying to manipulate, a surgical needle. It needs to be much more precise knowing where it is. Similarly, with mapping, if all you need to do is navigate from the bedroom to the kitchen, you can be very, very coarse in representing a world. But if you need to really find and pick, sort out objects in clutter, you need a much more fine-grained representation to it. In this talk, though, I'm going to be focusing on dense SLAM. Uh, SLAM has naturally seen lots of research over the years, and there are several paradigms. There is sparse SLAM, which is quite popular for real-time performance on robots. And what sparse SLAM means is, given a set of images, your map is going to be a sparse collection of interest points or features from all of those images combined. Like in each image, you detect some feature, and features are usually points or maybe even objects of interest. And only those sparse features constitute your map. All the other pixels in image are just discarded because they're considered irrelevant. Dense SLAM is just the other end of the spectrum, where every pixel in your image is treated like a part of the map and is reconstructed. So that's the paradigm I'm working on. And SLAM, as you can see, is a quite useful task for robots. Looking at some of these examples here, most of these robots on the top, they need to know where a particular object is in order to manipulate that. For example, this robot needs to know where the ball is in order to bend down and pick it up. Similarly, the Baxter. And autonomous cars, they need to know what's around them, where the other cars are, and where they are with respect to like a global map so that they can get you to your destination. And even the Spot Mini shown here, it needs to know where the door handle is and where, how it can extend its arm to open the door up. As you can see, SLAM is never meant to be an end goal. Like traditionally for last 20 years or so, people have looked at SLAM as being a central problem in robotics, where you just try and reconstruct the environment as densely as possible or like as accurately as possible, depending on which school of thought you're from. And once you reconstruct the environment and you have a estimate of where the robot is with respect to that map, SLAM is usually considered done. But as you can see here, SLAM is barely just scratching the surface because you need SLAM, but the task is what comes next. In other words, SLAM is never the end goal for a robot. Like for a self-driving car here, the task is never to reconstruct the world. The task is to drive safely among obstacles. So SLAM is a tool to do that, but it's not the only tool. And also another point of contention is SLAM somehow needs to be integrated with downstream tasks. So the kind of a map you reconstruct depends on the task that you're doing. If all you need to ever do is navigate on this road without hitting other cars, you don't need to reconstruct, every tiny window of this building and maintain a dense map of a city at, kilometer scale or several kilometers if it's like a section of a city. So with all these assumptions out of the way, we can start getting into more of the meat of today's talk. So when I say dense SLAM, I'm referring to the paradigm where you're reconstructing every pixel in an image as part of your 3D map. As you can see on the videos or GIFs playing on this slide, in this, there's like a huge trajectory a camera is taking over, and you can see the images here, and you're trying to put all of them together into one consistent, dense map of the world. And these maps are usually metric in the sense that there's a direct mapping or direct relation between each point on this map and some real world units. So
Krishna, I have just one quick question. Why is the reconstruction needed? Why isn't just the image? Let's say you have a robot, you have a camera on it. Why is that the image not sufficient? Why is the reconstruction process needed?
So that's a good question. There's a short and long answer. I guess the short answer is it depends on the task. And the longer answer is, let's say, if you want to plan or if you have a manipulator that needs to plan a trajectory inside an environment, there are well-developed techniques that operate if you have a known environment structure. Like if you know the 3D map of the environment, planning around in 3D makes easier because that's the actual workspace of the end effector of the robot. But
Okay.
if you had images, then you need some sort of function that plans on images and not on 3D maps. So, I mean, the way you can look at it is if you have 3D maps, then planning in 3D is more of a geometry problem where you need to find like the shortest path subject to a certain geometric constraints, like you can't hit obstacles, and you'd have some kinematic constraints of the robot. The robot arm cannot move or twist in arbitrarily different ways. It needs to obey some common kinematic constraints of the robot, and it has velocity or torque constraints and so on. They've been classically studied in 3D, which is why 3D maps were or they still are a thing. Another application I can immediately think of is augmented or mixed reality, where you actually want users to be able to interact with real world, and the real world out here is in 3D. So maintaining a 3D representation gives you.
Yeah, there it makes sense, but just for navigation, I was wondering why a reconstruction might be needed. Yeah, there it makes sense. Yeah, thank you.
So yeah, like the short answer eventually is it depends on the task, and not all tasks need dense metric maps.
Understood. Understood. Thank you.
So that's again one question I think very deeply about as to what kind of maps are needed for a particular task. But one aspect, that's one aspect I just try to brush off in this work and assume uh, it's sort of an assumption that 3D maps are needed for a few tasks. And for
Understood.
those tasks, I want to see how SLAM helps and where learning and SLAM can intersect.
Got it.
So naturally, with the success of deep learning based approaches in processing, images or speech or text more recently, uh, a natural question is how do these techniques even extend to SLAM? Because if you look at image classification or object detection, most of those processes seem to be, in a way, they make the IID assumption in that all data points are identically and independently distributed. So you're equally likely to find as many objects in the next image as you are in the current image, and so on. But that assumption is not really true, especially in robotics tasks where robots move sequentially within the same environment. So your next image is very likely dictated by your current image and your current action. So uh, I'm just trying to outline in this slide some challenges that deep learning, or rather SLAM, poses for deep learning systems. Like a lot of deep learning systems have this IID assumption, which is violated by SLAM uh, because it's a very sequential process. And also, if you think about the long horizon nature of SLAM, after, let's say in this room, after a point, you're already looking at things that you've seen before. So you need to be able to recognize and exploit that fact. And then modern SLAM systems, they're very, very heavily engineered. Like they've taken years of engineering to arrive at these SLAM systems. I'll probably present the short sketch of a pipeline of a
Yeah,
typical
sure.
SLAM system. So all of these engineering that's gone into designing SLAM systems that makes things very tricky to interplay with deep learning. And then there's always one question uh, as to what inside of this entire SLAM system needs to be learned. So do we need to learn everything end to end, or is there parts of the SLAM system that need learning and other parts can still be classical? So if you look at the initial classical versus learned analogy for the SLAM setup, classical SLAM usually involves two processes that can, at a lot of times, interact. You have localization that determines the pose of the robot with respect to a map. And then you have mapping, which, given the robot's pose, determines what is around the robot. So in SLAM, both of these problems need to be solved simultaneously, which is why it's popularly referred to as a chicken and egg problem, because you can't solve one without knowing the other. And since that's all, each of these individual problems are quite hard themselves. So trying to solve them in conjunction just increases an order of complexity. But
Krishna, we have one question. Can you take one question from the
sure,
audience?
yeah. And
Rahul, go ahead. Rahul, please unmute yourself and go ahead. Rahul. Rahul? Okay. Rahul asks a single. Yeah, go ahead, Rahul.
So in SLAM system, is it okay to use a single image, or we are using stereotype imaging
so
for construct 3D map?
there are several SLAM systems based on the kind of sensor setup you're using. Popularly, a lot of smartphones or maybe even drones, they use they used visual SLAM up to an extent, or monocular SLAM, which means they just have a single camera from which they capture the world, and as the drone keeps moving around, you get more and more images which you want to like fuse into a coherent reconstruction. But single images, or like monocular cameras to be more precise, they have scale ambiguity, which is simply like if you see an object from a single image, you can't really estimate its precise size in meters. So there's always this ambiguity of scale, uh, which is why they're not really useful if you want to do metric planning or task execution in there. So a lot of people now use visual inertial SLAM, which means in addition to a camera, you have something like an IMU. The accelerometer and gyroscope, they help you, especially the accelerometer, it helps you resolve like the scale ambiguity, because you now have a sense of gravity, and then that tells you how much you're moving per second. So you can use that to reconcile the amount of motion in image space. But there are also
Rahul,
other ways to do it, where you have like stereo cameras, or in this particular paper, I'm going to talk about RGBD cameras a lot. Cameras
yeah.
like the Kinect, which directly give you a depth stream output.
Rahul, does it answer your question?
Yes, yes.
Okay, please stick
Thank you.
around for the Q&A. Krishna will go into the paper. Yeah, please go ahead, Krishna.
Sure, yeah. So again, classical SLAM versus what many people are calling is deep SLAM. Uh, the idea, or the perception a lot of people had at least 3 years ago or so, was you could simply throw a deep net at SLAM and then you could get it to learn to simultaneously estimate robot poses and maps. And it seems like the community tried like quite a few approaches. There are a few papers out there which are trying to just predict a map and like a camera trajectory from a sequence of images. But an open question that's been debated quite a bit is, how do these representations need to be? Or like, do you just have a single deep network, or do you actually separate tasks like in localization mapping? So there've also been a set of approaches which try and separate localization and mapping. Deep TAM, or deep tracking and mapping, is one such paper that comes to mind, which tries and slices this into two different modules, each performing localization mapping. But in this paper, what I'm trying to do is, can we take the architecture of a classical SLAM system and try to impose that inductive bias into a usually like deep network or a learning based setup? So can we like faithfully use a lot of components from classical SLAM and then figure out only places that require learning and learn those modules instead of learning the entire pipeline end to end? So that's the big question I had sometime last year. And to answer that, uh, I started building a classical SLAM system, but in a language that supports automatic differentiation. Like you might have used PyTorch or TensorFlow. All of these are subset or Python libraries that support automatic differentiation. And one big use case of automatic differentiation is deep learning or backpropagation.
So when you say automatic differentiation or differentiation, what exactly do you mean? Will you touch upon that?
Yeah, there is a few slides.
Okay.
I'm
Please
just
go
going to get there
ahead.
soon. So in my view, like differentiable SLAM, or GradSLAM as I call it, which is also the title of this talk, is one way of bridging this gap or finding this middle ground between classical and learned techniques. And the basic reasoning, if results from Taylor expansion and computational graphs. Like if you think of SLAM or RGBD dense SLAM as a purely mathematical function, then SLAM is something that takes your sensor data. Your sensor data could be kind of anything. In this case, it's RGBD images, but for visual inertial SLAM, you could have images plus IMU measurements and so on. And you pass this through this SLAM function, and that function gives you a state estimate. I'm calling it M here, but it usually comprises of the trajectory of the camera and a map of the environment. So from a purely functional view, you can just write something of this sort where SLAM is a function operating on the sensor data and giving you a state estimate. So you might know from like calculus that any function, even if it's nonlinear, as long as it's differentiable, you could do a Taylor series expansion of that function. So, you know, if you have f of x, y equals f of x, you could do y plus like f of x plus del x is f of x plus f dash x, or the gradient of f times delta x. So that's basically the scheme we try and apply here, which is if you try and take RGBD images and you slightly perturb your sensor data, like, or here you can see that this part, the picture on the wall is cut out, and this is like perturbation. So if you perturb your sensor data by some delta S, then your map should change by M plus like gradient of the SLAM function with respect to del S. But the critical thing here is that you need this function to be differentiable in order for this approximation to work. Since it's not naively differentiable, because SLAM consists of a lot of non-differentiable components, which we'll also talk about, that's the reason GradSLAM was conceived. Like, we wanted to build a SLAM system that is fully differentiable so that you can compute the gradient of a SLAM system. So if you think about the analogy with gradient of a function, the gradient measures in a way the rate of change of that function. So if you change one of your coordinates by some delta, how much does your function change by? And similarly, in the context of SLAM, if the entire SLAM system were differentiable, we can answer all sorts of interesting questions, as if I were to take one pixel in this particular image and perturb it, you know, change it to completely black or completely white, how much is the map going to change by? Is there a question?
Go ahead. No.
Yeah,
Sure,
so
thanks.
the question is that, right, but that has been answered by Ganesh in the chat. The question was through differentiation, maybe is it like checking for the relative pose change in between the time instants?
So in theory, you can differentiate with respect to most of the quantities that are input to the SLAM system. So in this case, it's just the sensor data S. And if your sensor data comprises only images, then you can get gradients with respect to the images. And if you were to have IMU measurements, and if the SLAM system were differentiable with respect to IMU measurements, then you can also get gradients with respect to the IMU measurements, which indicate how do the IMU measurements need to change in order for the final trajectory or like the final poses or maps to match a particular value. Like another interesting application or a thought exercise would be, I have this lampshade in my map. If I needed to completely get rid of this lampshade, what in my image needs to change? So you would have a video sequence, and if you want to get rid of this reconstruction, it's somewhat intuitive to imagine that you need to get rid of all light shades in all of the images. So that's the kind of relationship a gradient would give us. So if you would ask a question in 3, like if I need my map to be something like this, what needs to change in image space? And this is something I'll also revisit towards the end of the talk, maybe with a few more illustrative examples. So if it's not clear even until by then, please feel free to like bring this up again. So one particular inspiration for us was the framework of computational graphs. If in most deep learning courses, this is probably one of the first few lectures that's taught. Like any computation that you have can be decomposed into a set of preliminary computations or primitive computations, each of which are atomic. So in this case, if you have a function that just takes, you know, or here, this is a multiplication node, which means 15 is multiplied by 5. And then or here, it's an addition node, which means 15 is added to 5. And you divide it. So this entire function represents 15 into 5 by 15 plus 5. This is just for a very simple function, but you could imagine all sorts of complicated functions being broken down into their very atomic components and being represented in such a computational graph format. And if you think about it, these computational graphs are exact manifestations of the chain rule. Like the chain rule of calculus is you can take any arbitrary complex function and break it down into, you only need to know a few primitive derivatives. And if you know how to differentiate each of these atomic blocks, you can differentiate the entire function. So you can have weird compositions of all primitively differentiable functions, and this entire composition is differentiable by construction. And these computational graphs are what are used in reverse mode automatic differentiation, which is quite popular in like modern machine learning. Reverse mode just means that you perform a forward computation until you get to a final value, and then you start back propagating from here and computing the chain rule backwards. And computational graphs have seen lots of success in especially other fields such as graphics or physics, where you can take processes that you really understand. Like rendering is a process that's very well understood. It's in graphics, there's been lots of study on rendering, and that's how a lot of movies or video games are made, by rendering uh, scenes that are synthesized. And it's been shown in a few recent papers that if you can approximate the rendering process by a differentiable function, so you have a 3D scene here, and in this case, the scene comprises just a single object. If you can differentiably render it, then you know you have a means of propagating gradients from the image back to 3D, which means you can now compute a loss function in image space and then propagate the gradients to 3D and then figure out how should the scene change in order for the image, rendered image, to match some target. So if this plane were rotated in some sense, then the differentiable renderer would give you gradients as to how do I rotate the plane in 3D so that it best matches the 2D silhouette. And similarly, there's been lots of work on differentiable physics, which particularly studies the problem of if I'm given a trajectory of, let's say, a dynamical system like a robot, can I actually figure out the parameters, the control parameters, or the physical properties that resulted in that trajectory? So if you can model the entire dynamics of an object differentiably, you can then back propagate to figure out either parameters of the dynamics or control parameters that help achieve like a target. So while in rendering and physics, there have been breakthroughs. Rendering, for one, is a highly non-differentiable process, because if you think about visibility as a phenomena, you can either see an object or you cannot see it. Or if you talk about occlusions, a particular pair of objects is either occluded or unoccluded. There's no, it's a binary variable. There's nothing in between. So it's an inherently non-differentiable process, which is what these differentiable renderers try to approximate by softening each part of an object. So if you think about graphics, each object is represented by a set of polygons, or here it's a set of triangles. Instead of typical rendering where each triangle is very concrete, like it's the edges of the triangle are completely they're in a way line segments. Anything outside that line segment does not belong to that triangle, and everything inside belongs to that triangle. So they create soft approximations of these triangles in order to make differentiable rendering possible. And in physics, you can think about contact as a phenomena that's not really differentiable. Like you're either in contact with the surface of an object, or you're not in contact. There's nothing in between. So softening contacts is one way of making contacts differentiable. There's also other ways which of making things differentiable. I'm not sure if I'll get to them in this talk, but yeah, in general, differentiable processes is an emerging field, which is quite of interest to me. But as we've seen for graphics and physics, I don't think this, the case for SLAM is very straightforward. So if we look at the typical anatomy of a SLAM system, or of a dense SLAM system, you start out with RGBD images. So I show one RGB and one depth image, but in fact, it's like a sequence of streaming images here. And the first step in any in a typical RGBD SLAM system is surface measurement, which is given this RGB and depth image, can we get a local approximation of the surface of the scene? So you know that there is a pixel here at a particular depth. Can you leverage the fact that pixels nearby in the image usually tend to be nearby in 3D, except at occlusion or depth discontinuities, and get a measurement of the local surface? So if you look at this patch in green, it indicates that the surface of the sofa is sort of one plane. That's what this indicates. And this surface of the sofa, this part, is another plane. And likewise, when you see the pillow or when you see the wall, the surface measurements tend to give you an idea of how consistent neighboring pixels in image space are. So we compute vertex normal maps, as we call it, where you compute vertices, which are simply X, Y, and Z locations of each each point image. And normal is a direction indicating which way is the surface oriented. And then you take a lot of these vertex normal maps and perform surface reconstruction. So this is where you move from image space to map space. Like your images are always pixels, and you have vertex normal maps that are defined over each pixel. And this phase is called 2.5D mapping, because you just have an image with an extended Z channel, or like with vertex and normal maps, it's still defined all of the image. But your maps in 3D can be in various representations. For example, you can divide the entire 3D space into a set of discrete voxel grids, and then each voxel could be a part of your map. Or you could think about having point cloud maps, where each the primitive element in a map is a point. Or there's also surface, where each primitive element is an ellipse of sort. So it's like a disk where you can approximate multiple points that lie on the same plane using a small planar ellipse. So once you have this local map, you try and fuse it with a global map. The global map is initially empty. Like in the very first frame, the global map would be completely empty. But after you have integrated a few frames, after you've seen a few images, the global map tends to be something like this. The global map consists of it consists of noiseless estimates, or it's like the best guess of the 3D scene geometry we have so far. So what you initially do is you take this local global map, and then you raycast it to image space, and then you try and align this local map to the global map. Like you're trying to align the current frame with the entire map that you have so far. And once that alignment is found, you know which parts of the current frame correspond to the lampshade here, which parts correspond to the sofa. Once you have that correspondence, you can now update the global map using information from this frame. And that's typically referred to as map fusion. And this process is usually repeated for each frame until you run out of, until the end of the video sequence.
I think,
yeah. Is there a question? Cool. So yeah, all of the red boxes that you see here indicate non-differentiable elements, or those are the aspects of SLAM that are non-differentiable. And in GradSLAM, these are actually the elements that we make differentiable. So there's processes like differentiable visual orometry, nonlinear least squares, and dense mapping, or raycasting, all of which are non-differentiable. And our sort of idea is that we could make all of these processes differentiable by making suitable approximations wherever. So how are we on time? I'm assuming.
yeah, you can go ahead. Yeah, go ahead. Anyway, you joined late, right? It's fine. Please go ahead. Yeah, please go ahead.
Yeah, so I'm guessing it's going to take 15 more minutes
Yeah,
at
yeah.
most.
Fine. It's fine. Take your time. Take your time. Yeah.
So yeah, like one of the key insights that we had in this paper was a lot of these SLAM components use optimization in some form or the other. And optimization, at least in the way it's used in SLAM, is non-differentiable. And just to give you an idea of why that happens, let's say you have a non-convex function, and nonlinear least squares just amounts to like, least squares problems involve finding a minima to this convex problem or non-convex problem, depending on how you cast it. And if, let's say you start here, you reach this minima, but if you start, this minima might be quite different from the global minima of this function, because it's very sensitive to initialization. And then there have been extensions proposed to simple gradient descent. So what you saw here was gradient descent. If you have an initial guess, you just keep descending the gradient of that function until you get to minima. But there are variants of gradient descent where, let's say, you start here, you can approximate the function by a line and then just project it here. So this is the Gauss-Newton method, which linearizes the function. And once you linearize, the least squares solution is convex. And you then relinearize the function about the new guess, and then you keep doing this until you get to a converged solution or until a predefined number of iterations. But with the Gauss-Newton method, the advantage is it's differentiable because all of the solutions are just, it's a sequence of least square solutions, but there's no convergence guarantees. You might even diverge, and it's also quite numerically unstable, which is why people propose this combination of Gauss-Newton and gradient descent, where you do gradient descent if you're far away from the solution, and you do Gauss-Newton if you're close to the solution. But this entire setup is non-differentiable because you're sort of, at each step, you're trying to see, am I close to the solution or am I not close to the solution? Like this is called a trust region method. If you think you're close to the solution, you keep doing Gauss-Newton, which is you keep taking larger strides towards the solution. But if you're far away, you keep taking very small strides. You do gradient descent. So we make this switching process differentiable by taking like a smooth, so this switching process, which is usually discrete, if you connect it by sigmoid-like switches, you might be aware of the sigmoid function, which is used in image classification and so on. So we basically, this results in non-smooth gradients, but when we smooth using a differentiable LM, we get smooth gradients.
So how does the smooth gradient affect the result in the?
So yeah, like if you had non-smooth gradients, you wouldn't be able to backpropagate through the optimization step. So
Understood.
in a way, you won't get gradients all the way to the input image.
Understood.
So if you look at the functions here, like at all of these points, the gradient is 0 because the function is constant. And at the point where it changes, the gradient is not defined because the left side value is different from the right side value. So smoothing this actually allows for you to have gradients over this region.
Yeah, Shambhavi, please go ahead with your question.
So two questions. One is when you said sigmoid switches, were they exactly the sigmoid functions or something different?
So they are what we call the generalized sigmoid or the generalized logistic function. If you look at this, this is one particular case of a sigmoid. Sigmoid is usually, it's restricted to be between 0 and 1. But you can think of a sigmoid which is scaled, like it may not be between 0 and 1. It can be between 0 and 10, for example. Or you can now start thinking about sigmoids that are translated. Instead of being between 0 and 1, they can be between -1 and 0. So all of these parameters in the logistic sigmoid function, they control where the sigmoid begins, where it ends, and how fast it grows. So a sigmoid is usually symmetric, but by introducing some non-linearities here in the exponent, you can actually control how fast it grows.
One more question. Can you switch to the slide where we were discussing the gradients?
Yeah.
Right. So here in the first graph where you have written non-smooth gradients, the gradients are absent, and in the second graph we have steep change. Like the gradients are with a steep change. So isn't it different?
So yeah, like when in this graph, the gradients are usually non-existent. That was one point I was trying to make, because over here the gradients are 0, and in these regions the gradients do not exist because your right hand side function value is different from the left hand side function value, so they're not really continuous.
But when you are smoothing, we are actually creating the gradients where they were not.
Yeah, so that's precisely what you do even in image classification, right? If you're classifying cat versus dog, the decision boundary, if you were treating it as a discrete problem, then you wouldn't be able to differentiate through it, which is why you use a sigmoid to create this smooth sort of decision boundary between two classes. So a sigmoid would actually give you some form of a real value between 0 and 1, and you threshold that sigmoid to actually go to whatever, like you pick a class based on the highest or based on thresholding.
Krishna, you are muted. Can you just unmute yourself? Yeah.
Yeah, so
Does it answer your question, Shambhavi? Yeah, okay, thank you.
so there's also processes like raycasting, which we make differentiable. Raycasting is taking a volume, a grid, and then projecting it down to an image. It's like rendering. Like you want to figure out where each voxel projects to. And the way you do it is you make it differentiable is shoot a ray through an image and then sum over the contributions of all these rays. So let's say these pixels are usually unoccupied, and then this one pixel in red is occupied. So along this ray, you just decay the function value based on the distance from the nearest occupied pixel, and then you just pool all of them to form an image approximation. And then the entire dense mapping process, as you, I guess I showed one huge slide where we were getting a local map and then trying to reconcile it with a local map and then fusing them. that entire process is made differentiable by using soft associations wherever possible. And then the surface measurement step, or even the alignment step, then made differentiable by using the differentiable nonlinear least squares optimization step. But once you put all of these together, like what you get is you can now backpropagate through the entire SLAM system. So there's been quite a few representations proposed in the dense SLAM community as to how you should represent your maps. Depending on the kind of representation, we implement like 3 different SLAM systems. One which is just based on truncated SDF or sign distance function maps. It's called Kinect Fusion, where your map is basically a voxel grid. So inside that grid, each voxel has a sign distance function. Like at each point, you store the nearest distance to the nearest surface. And then you can do a post-processing step where you extract the surface from the reconstructed map. Since it's voxel grid, it's usually determined, it has a fixed resolution, and you can see that some artifacts are still showing up here. You can see sort of line-like artifacts because you have discrete voxels. And on the other end of the spectrum, we have ICP odometry or ICP SLAM, where you just take each RGBD image, convert it into a point cloud, and you keep adding new points to cloud as soon as you get new images. So this is called ICP SLAM, where we basically just keep accumulating all images that have, all points that have ever been scanned. There's also middle ground where you can do more efficient than ICP. For example, if you have a 240 by 480 or 640 by 480 image, you can imagine there's about 120,000 points per image. So if you just accumulate 10 images, you're talking about 1,200,000 points. You can be more efficient and then reuse points, which is why we use circle maps, where multiple points are merged into a single circle if they're close enough and if they have similar orientations. So this means if you have a planar patch, whatever new points you get for that patch are being reused. And that makes point fusion or circle maps more efficient compared to the other alternatives. So these differentiable SLAM systems, they perform quite similarly to, in terms of reconstruction quality, to their non-differentiable counterparts. But the added advantage is now they're fully differentiable. You can backpropagate through the entire SLAM system and get gradients useful for your task. So this is a non-differentiable point fusion reconstruction and ICP SLAM reconstruction versus a differentiable point fusion ICP SLAM reconstruction. And the good thing with these differentiable SLAM systems is you can just run them on your GPU without really worrying about all of CPU, GPU bottlenecks or run times. Like one key result of this paper, I guess this is really the main slide. That's the takeaway point, is we can now measure the contribution of each pixel to a 3D map, something which was not previously possible. So let's say you have an RGBD image. I'm not showing the depth channel here, but you just get a sense, like this is the RGB channel. And if you run GradSLAM through a sequence of these images, you get a somewhat noisy reconstruction because of sensor noise and other things. If you compare it with a very clean reconstruction, like reconstruction where images have no noise, we were doing this on a synthetic data set, so it was possible to get images of the same scene with and without noise. So this is a reconstruction from noisy images using GradSLAM, and this is a reconstruction obtained from clean images. And these reconstructions are voxel grids. So if you directly subtract these two voxel grids and backpropagate through the entire GradSLAM system, you sort of see gradient magnitudes. I'm not sure how clear this image is, but you should be able to see
Yeah, we can see
edges.
across. Yeah, across and multi. Yeah.
Yeah, so this cross is mainly due to the camera frustum projecting outward. So this is where the camera center is, and these are rays that are shooting sort of outwards from the camera center.
Mm-hmm.
There seems to be a lot of noise along these rays because it's also quite natural given that these are the extents or bounds of reconstruction. And there is lots of noise around edges. Edges seem to have more noise in this reconstruction. So these gradients are visualized in image space. Like on this image, these edges are where you have the highest error at. Now we repeat the same experiment, but this time we just cut out a chunk of, we just cut out the square from the center of the RGB as well as the depth image. Since the square is cut out, you'll get something like this. This is a hole in the reconstruction. And now if you compare this again with the same clean reconstruction and you backprop, you now get a different image. I hope you can see the center part where you actually have now this square affecting gradient
Yeah.
magnitude.
Yes. Yes. Yes.
If you take the difference of these gradient magnitudes, it's quite easy now. It's clear to see that this is what causes the largest change between these two reconstructions. So if you have this sequence of images versus this sequence of images, it is these pixels at the center of the image that cause the greatest change in gradient magnitudes. And like this is probably a much better visualization where we have an occluder. This time it's in front of the camera. It's not a hole, but rather it's a block that is in front of the camera. And comparing this with a clean reconstruction gives us a sense of which pixels in the image space contribute the most to image space gradients. So it's like saying how much is each pixel contributing to reconstruction error. All the parts of the scene which are quite static and don't move around and are not occluded, they are not at all erroneous because they match very well with this reconstruction. But parts that are occluded by the square, they don't match up and they show up as errors, and that's the gradient. And this to me is key because we can now use this gradient to do all sorts of interesting tasks. Like given a 3D reconstruction, we now have a way to answer how much is each pixel impacting. And once you have that gradient information, you can add that gradient to the image with some learning rate and say, now my image is much closer to what's expected by the loss function. So you can keep training any sort of any task that you want to do in image space using gradients through the SLAM system. And this is probably the key slide. So I pause for a bit and see if there are questions. The remaining slides, they'll probably just take 5 minutes to go through, but I'm happy to take questions.
Yeah. Any questions, guys? Please go ahead now. Let me just, yeah. Any questions from the audience? You can unmute yourself and go ahead. Okay.
Sir?
Yeah, go ahead. So,
Yeah. So this was done for the RGBD images, correct? So,
Yeah.
and even for the RGBD, you're going to take for almost, it is like you're comparing for each pixel, correct?
Yeah.
So, can a similar approach be done for a LiDAR SLAM? Because that is the point cloud image, right? So, can a similar approach be applied there?
Yeah, so I don't think there would be a problem directly applying something very similar to LiDAR images because in LiDAR SLAM, what you would do is you typically take multiple LiDAR clouds and align them using some form of ICP or iterative closest point. You're just trying to align point clouds there. And that is something we already make differentiable in GradSLAM. So as long as you can align a lot of these images, you can backpropagate through them. So for LiDAR, it would work, but for monocular SLAM, it's a different story. I don't think it would work directly there, but I'll probably present a sketch of how you could get there.
okay.
Yeah.
Does that answer your question, Saurabh?
Yeah, yes, sir.
Okay. Rahul, please go ahead. Rahul. Okay. Rahul, I thought he had a question. Okay,
Sure.
please
Yeah.
go ahead.
Okay,
Yep.
I'll
is
just.
it?
Yeah, Rahul, go ahead quickly. Yeah, we can hear you. Go ahead.
So we are considering one blank spot, right? Hello,
Yeah.
Yeah,
Like.
go ahead.
hello.
Yes, we
And
can hear you,
what are the
Rahul.
advantages in the gradient? Okay,
So yeah. I
so we are
guess
considering some.
that's a good
Yes,
cue
yes,
for
yes.
me to like move to the next slide. I'm in the next 2 or 3 slides. I'm going to like try and demonstrate that these gradients are useful for some meaningful tasks that we'd like to do.
Okay. Okay.
So
Stick
the
around, Rahul. Yeah.
so there's like we try to run this on real data as well, and as you can see, real data it's much more noisy, so it's not as cleanly looking as synthetic data, but it still works quite well. And yeah, this is something we were running off. This was thanks to like Ganesh and some of his colleagues there at CMU who grabbed this data set right in time for the paper submission. So yeah, we were quite intrigued to see it worked without a lot of tuning directly on real data
Yeah, it
captured
worked
from a
out of the
real
box.
sense.
It worked right out of the box. It's just kind of a cool thing.
Go ahead. Ganesh, please go ahead. We can hear you faintly.
Okay, is it not very clear?
Yeah, now it's fine.
Yeah, I was just saying that like the cool thing about about the system itself is that it just works right out of the box. Like we in this case just like took a real sense camera, collected this data, directly tried it out on the system, and it was able to create like a faithful reconstruction without much issue. So like at the on the sort of practical side, as a fusion system, it works well. But on the theoretical side, you also are able to get the gradients with respect to input images and actually see the effect of every pic. I mean, we'll actually go into that. I don't know if in the next slide KM has that representation, but like there is this one part where you can actually say which points are affected for each image that comes into as a video stream to the input.
I think I have that.
Yeah, so
I'm gonna
that's
get
very
that.
cool.
Yes.
So yeah, like we show a few applications of this. So if you look at this panel on the left, what we're trying to do here is take a series of 4 images, 4 sequential RGB and depth images, but the first image is corrupted. Like you just take a random depth, like a constant random depth for all pixels, and you just take some random noise for uh, each RGB channel. And just by running a very similar scheme as shown here, where you try and compare the noisy and clean reconstructions. But in this slide, we're doing it for a differentiable point fusion SLAM system instead of a kinect fusion system. Like we have a sequence where 4 images look somewhat like this, versus, and in that the first image is corrupted to be random RGB and like constant depth. And just by back propagating and getting the gradient information, we are able to update the initial image in about like 400 iterations of gradient descent to get something very close to the real image. So we're able to recover, our gradients are able to give us meaningful information about RGB as well as depth. So it's like from noise, we are able to get back to the original image. And on the right, we show the ground truth. Similarly, on in this bottom panel, we just use a different noise pattern. Instead of using completely uniform, we use an additive noise to depth channel where we take the ground truth depth and we perturb it a bit. And we're still able to recover RGB as well as depth quite accurately. And you can see that the colors of each book, they're retrieved. And then you can also see the edges here, which is quite important. And so on. Like other interesting artifacts are you can actually see you can actually fill in information that's missing even from the sensor frame, because you now have access to multiple views. If you look at the depth image here, you have no depth measurements from this part. But by running this system through GradSLAM, you can fill in depth information from this part by pulling in information from a few other views. So these are a few things. I'm probably going to skip this slide because the next is probably more interesting. In this slide, we just show a reconstruction where we can randomly click on a point, and then we get the influence of, we get the gradient with respect to that point. I don't know if you can see this clearly, but a large fraction of the image gets shaded here. So if you click a point somewhere here, in the image, so these are image 1, 2, 3, and 4 in that sequence. And the last image always has the least effect because it's the most recent image. So it's not been fused with the other 3 images. But if you look at this pixel in this image, it might have contributed, it might have received contributions from a larger area in this image, which in turn will have received contributions from a larger area in this image. This analogous to the receptive field in CNNs, where as you keep going back, you can see which parts actually contribute to the reconstruction of that pixel. So we think that's a key advantage of GradSLAM, and that can open up a lot of new applications in at least gradient-based learning. So you can use these gradients for learning tasks. We showed like single image depth estimation or depth completion task on the previous slide, but arguably there's just a lot more you can do. And we're working hard to release this as an open source SLAM package. And I get like quite a few questions on when this is going to be out, and we're trying to get it out as soon as possible. Like we just extensively want to test things and just finish up a few other formalities. But yeah, we want to make available a differentiable SLAM package for PyTorch where people can basically load up their favorite data set, or here it's the scannet data set, and you can run differentiable SLAM by just a few lines of code. Or here it's quite simple. You just create a data loader for your data set, and then you create an odometry provider, and you create your own SLAM algorithm. We have point fusion, kinect fusion, and ICP, and then you can visualize them. So yeah, this is something we're working hard to release. But there's also arguably quite a few challenges to GradSLAM. That's, I guess this part is something I never get to talk about in some of my other talks, so it's worth spending some time here. So as you can see, GradSLAM, since it maintains the entire computational graph for gradient computation on in GPU memory, scaling to larger environments will be an issue. Like if you had 100, like more than, let's say, 100 seconds of video, for example, or even like 400 to 500 frames, it becomes very hard to scale. And there's also a question of vanishing gradients. Since you're unrolling this computation graph for quite a while, you want the gradients simply vanish before they get to the input image. And this is something we never really got to answer, just because scaling has been an issue. Like even before we run into vanishing gradient issues, we usually hit GPU memory bottlenecks. And one other core, like let's say assumption here is you have 3D supervision, because GradSLAM is a SLAM system that takes in images and gives you 3D maps. The loss function or supervision must be defined over the output space, which is 3D. So you need to define a loss function over 3D maps, which means you need 3D ground truth. And that in some sense is limiting, because the assumption of 3D ground truth is quite strong. So some of my current work is trying to get around this need for 3D supervision. And then there's also the other open question of extending to sparse SLAM or relocalization. monocular cameras, that is something I don't have a clear answer for. But my best guess is we need to resort to some form of single image depth estimation, which can be again trained using GradSLAM. And then relocalization is a form of attention operator in map space. So yeah, this is like the broad, this is a broad overview of GradSLAM, its strengths and weaknesses. And this is really the last slide of my talk. So I open this up to questions.
Very good talk, Krishna, and thank you, Ganesh, for joining in. Very informative talk. Thank you very much. We'll take few questions. I just had one question. In the paper, can you pull up the table you had where you compare, if you have the paper with you?
Yeah, let me just try to pull that
yeah.
up.
So others, please post your questions in the chat so that Krishna and Ganesh can answer it. Thank you,
From the
Ganesh. Thank you for your time.
Yeah, thank you.
So we'll just pull up the table. That is very interesting where you compare. Yeah.
Let me share my screen.
Yeah. So you have the paper.
Can you see my screen?
Yes, yeah. This paper. So what are you trying to? Are you trying to compare with? Yeah. What is happening here? I was just wondering.
So, is it this table that we're talking about? Is this
Yeah. This table. Yes.
Okay, so do you want to take it or could I take it, Ganesh?
Anybody's fine. Anybody's fine.
Okay. Yeah, like this table, we're just trying to compare. Like the point we're trying to make is GradLM or the differentiable LM is similar in performance to LM. So what is, since we have this entire LM pipeline differentiable, do we lose out on performance? That's the question we are trying to answer. And we find that there is no significant gap in performance between the non-differentiable and differentiable variants. We see that in some scenarios, GradLM performs slightly better, in some standard LM performs better, but both are, the differences are not statistically significant.
Like the question
And we
is
also
like
wanted
how
to show,
mathematically accurate is GradLM to they're adapting Levenberg Marquardt to make it soft differentiable. So
yeah,
we are
like,
trying to check the mathematical accuracy of the operation over here.
Very good. Yeah. Very interesting, and also really great FAQ at the end. I had never seen an FAQ section at the end of the paper. It was very good touch. I think it was there from your GitHub site. I saw the paper version where you had a FAQ. Very good. Anybody, if you have a question, please unmute and go ahead.
I'm going to continue sharing the paper. So if anyone
Yeah,
has any
yes.
questions from the paper, they can
Very good. Yeah.
just point
So,
to it.
okay. Please type in your question. Meanwhile, can you just talk about raycasting? What do you exactly mean by raycasting?
so yeah, like in Kinect Fusion, especially, like Kinect Fusion is the only SLAM system inside the entire suite that uses raycasting. So when they have a new image that comes up, from the current 3D map, they want to synthesize a probable new image. Like they want to get an idea of how the new image might look like. So they take the current map and they render it out to an image. And since they have a volumetric map, a voxel grid map, they just do a raycasting step to synthesize images. And they compare that synthesized image with the actual image that you get for pose estimation.
Okay. Good. And also you have in a place where you're calculating values of R1 and R0 and you're subtracting them, and then you find out whether it is damp, you need damping or not to undamp. Yeah, what does it mean?
So yeah, maybe Ganesh,
This
you want to
part,
take
right?
that?
Yeah.
The GradLM question.
Yeah.
You mean like
Yes. Here, the value of R1 in the second, just below the graph.
Sure.
Where
Yeah,
basically this portion.
Yes.
So, the intuition here is or traditional LM or Levenberg Marquardt is a trust region technique. What that means is if the algorithm thinks it is within a trust region or within a basin of convergence for the function, it will start taking larger steps towards the minima. And if it thinks it is far, it starts reducing its step size. It starts taking very, very small steps. And it thinks before taking each step as to whether that step will take it outside of the convergence basin. And that is the look ahead operation here. And
So
like
damping
R1
refers
minus
to
R0.
damping refers to it continuing with the iterations or what?
Yeah, damping refers to the damping of the step size. So if your step size was of unit length, you would damp it to take half the step size.
Half the step
Or
size.
the damping is usually multiplicative. Like if you think a step size of 1 will take you outside of trust region, you try a step size of half and see if it still keeps you inside. If that takes you outside, you try a step size of 1/4, 1/16, and so on.
Yeah.
So like that step size is usually determined by the look ahead value of the residual minus the current value of the residual. So you have the look ahead value R1 and the current value R0.
Got
So
it.
if taking that step increases your residual, you want to take a much smaller step. You want to damp. And if that does not increase your residual, then you want to take a step. And you also want to undamp. Like next iteration, you just get a little greedy and take a bigger step. That's like the damping undamping.
Very good, very cool. And you also perform
So
global.
also just to add, this is exactly the point that sort of we had to ensure to make it differentiable, because this is an if operation.
Understood.
So
Yeah,
checking if your error is increased in the next step is an if operation, such that we can change the value of lambda, which we cannot explicitly allow for calculating gradients. Uh, so to make it sort of smooth over here is where this R1 minus R0 decides what the next value is going to be.
Yeah,
That
yeah,
makes
yeah.
sense.
Yeah, like
Yes.
it'll be very simple to think if R1 minus R0 is greater than 0, let's say you undamp, or if else you damp. Like this is just a small bit of code that's non-differentiable. I mean, you can get a gradient to it, but you won't get gradients with respect to the damping factor, which is why instead of doing this if, we reduce this if to a smooth sigmoid like switch.
Yeah.
So the sigmoid naturally has a continuous balance between being close to 1 or being close to 0.
Understood. Now, one last question. I have one last question. When you say global pose estimation, what do you mean by that? Global pose estimation?
So
yeah,
global pose estimation with respect, so whatever the reference frame is, estimating the pose of, in this case, the camera in some global reference frame.
So,
like in SLAM, there's always this notion of loop closure or place recognition. And what that means is after a very long trajectory, you come back to the one place. You want to recognize that you're at the same place and like reuse information that you computed before. Otherwise, the map will just sort of drift. If you're going in circles, the map will start looking like a spiral instead of looking like a circle. So the global pose registration or global map registration means that at every instant, we're taking the entire map and registering with respect to the current frame. So that's it's a global process, and that can only be done for small maps. You can't do it for very large maps because it'd be very cumbersome to take an entire map of like 1,000,000 points and keep registering it to every frame.
yeah, yeah, yeah. Very good, spectacular. Any other questions, Swaroop, Shambhavi? Any other question?
Yes, sir. Yeah. Right now, this thing which you have explained for was for the map, correct? So already, as Ganesh has answered in chat, I wanted to ask if your robot is moving in an environment, and for the control system of the robot also, like the control signals of the end effector or whatever. Simultaneously, is there any system tried out that you're predicting an image, uh, using GradSLAM, and then using that to adjust your control output, something like that?
So I mean, we've thought about it, but we've never really like found time to work on the active aspect of GradSLAM. So there's a lot of work done in active SLAM in general, where the robot chooses its next action to minimize some metric, like to maximize information gain or to reduce the uncertainty in its localization. So robots tend to choose their own actions, but yeah, GradSLAM is in a way passive, like you operate on pre-recorded video sequences. But definitely that's an exciting new area. And to be honest, we haven't explored a lot of that, but
And like
that area has great promise.
at some stage, looking at embodied navigation or this area of embodied navigation that you're talking about is like it's a very relevant and upcoming area. So maybe looking at some aspects of embodied navigation and how that might help with, or that how we can combine that with SLAM systems is like an interesting area in itself.
Okay, thank you, Saurabh. Any other question? I think no other question from the audience. Thank you, everyone. Thank you very much, Krishnamurthy and Ganesh. It was very, very useful for us to get information at such depth. And thank you for your time to show us all the experiments that you conducted. It was very informative. Thank you very much for your time. And hopefully we'll see more publication from your group.
One more question. How much time did all of the research on this took?
That's
It's a loaded question, loaded nuclear grade question.
I don't know how to answer that. KM, what do you want to say?
Yeah, I mean, it just
You
took.
can say the experimentation alone, how much time the experiments took, maybe.
I mean, I guess, or here in this work specifically, the hardest part was coming up with this idea in general, but after we came up with this, implementing was not a big pain. But like refining this idea itself was a thought process. We've had very similar ideas in the space for about 2.5 years, but then didn't work on, like some of them did not work out and some of them did. Eventually, I guess just 1 week or so, sometime in summer last year, that's when we really concretely identify that we need to make a differentiable. That's when things started moving quite fast.
And also, you mentioned that a few of the results were provided just some time before the XCCV talk. So, is the process of this research paper writing iterative? Like you get more results, you add more, then you think something is missing, then you again get more results, or like was it all planned beforehand?
It definitely is iterative, and I guess it's in a lot of ways it's deadline driven sometimes. That's while that's unfortunate, I guess that's how it's been in the publishing circles. Like before the deadline, you try and rush and get to some sort of viable product, but you're always I find myself and from a lot of students that I observe that your paper is always 80% baked when it comes to submission. But
I was right.
since everything is an archive now, it's common practice, I guess, to have multiple versions of your paper. And like we are actively working on updating this GradSLAM version soon. Like when we release it, we also want to like update the paper with some of our newer experiments, which yeah, they're only in the video but not in the paper.
Right. I regretted missing the session at ECCV for your paper, but this talk has been so detailed, so from the scratch, like the thing has built up so well. So thank you so much. It was very good.
Just last two questions, Krishna. Like, what were the reviews? Anything specific from the reviewers when they reviewed this?
Like for one, the reviews were actually quite detailed, and I really enjoyed reading those reviews. And most of them were quite positive. I guess these were among some of the more positive reviews that I received for any paper. But there was also like a lot of skepticism, and that was something which was expected. Like in a 6-page paper, we couldn't pack in all of the details. So that was something the reviewers were asking for, because a lot of details seem to be unclear. I hope like sometime later we just submit off to a journal where we can not worry about space.
Yes. And also, you also, I believe, review papers regularly. What do you look for in papers? Like when you just skim the paper, do you look for any key points that?
Like yeah, like whenever I read a paper, I think I look for whether that paper gives me a new insight, something that I've not known before. And I personally think results or even novelty, they don't matter a lot. Like there's a lot of papers that show A plus B is new, where A is already done before, B is already done before, but you're just joining together. While a lot of people think that's not novel, I think sometimes it depends on the insight. Like if that paper is really, yeah, if a paper leaves you with more questions than answers, and in a good way, then yeah, those are the kind of papers I really like reading.
Good.
Right. One more question. So I wanted to know that recently, being an undergrad student, I have recently started exploring this domain. I found out that many papers were more or less application based, like using CycleGAN to solve a problem in a domain in which earlier CycleGAN was not used, and using CycleGAN yielded better results. So what do you think about such publications?
So it again depends. I'm equally positive about both. And if you look at research, there's also the more theoretical side of research. I tend to classify myself as a more applied researcher, and being in robotics or computer vision, I think it's a distinction as to whether you want things to work out in the real world, in which case you have to become more applied usually, or if you want to explore some of the more academic style problems. While I do a mix of both, I'm more leaning towards the applied end, where I sort of like a lot of engineering challenges in bringing
I
systems
think
up.
what Shambhavi is getting to at is an architecture used for multiple application, and each like architecture and application was a separate paper. Is that what you're asking, Shambhavi? What do you?
Somewhat, yes.
Yeah, I mean, I've seen some of these papers start getting diminishing returns over time. So in research, especially if you're planning a long career ahead, I'd argue for having some sort of speciality, or like trying to get a niche of your own. For example, I tend to work a lot on differentiable processes, like physics, graphics, or in this case, SLAM. So that's been one of my thrust areas and things that I get interested in. But if you were to take, let's say, a paper and start applying it to new scenarios, I'm guessing sooner or later there's going to be a time where this area is so uh, like spread out, and there's lots of papers that novelty factor reduces. I mean, you can also see those diminishing returns in computer vision research. The last 3 years or so, there's been a lot of uh, reduction in papers that do pure supervised learning. But when in 2012, when AlexNet and everything came out, everyone were applying, the same network architecture to different problems.
Also, like reviewers have caught on now. So those, like for example, uh, taking like a supervised system. So like when we started off with GradSLAM as well, one of the sort of papers that we were looking at was like PoseNet, papers that directly supervise to find the pose, or like directly supervise to estimate the 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 transformation between two images, for example. It was still novel at that time, and it was acceptable because it was still new. Now more and more, as more and more people are catching on, the reviewers are catching on as well. So there's a point where they'll be like, okay, this is just not novel enough. You're just taking a network and applying it directly to this new input, for example.
Good.
Nice.
Yeah.
One more question is there.
Rahul, yeah, one last question. Please go ahead and we'll end this. Rahul. Okay. Rahul. Okay.
Hello.
Yeah, go ahead. One last. Yeah, we'll let them go with one last question. Yeah, go ahead. We can hear you.
Like if you just have questions or generally want to chat, we could maybe just end the recording and then we could
Yeah, yeah, yeah.
continue on. Like I'm available for next,